All right, we are here to work on Chapter 3 problems. The first question in the extra problems to try is number 18, which is drawing the conjugate base for each of the following acids. Here you want to look and see which one is the most acidic proton in the molecule. And in the situation of E, our most acidic proton is this H on the carboxylic acid. So the conjugate base of this one is when the H is removed. And if you wanted to practice your mechanism drawing, you could do that as well. So I have the negative charge on my base. The negative charge will grab the proton, and the electrons in between there will go on to the oxygen. So I have an O- as my conjugate base. In this example here with NH4+, again I have a base with a negative charge. If it helps to draw the nitrogen out with all of the hydrogens and the bonds, you can do so. And the negative charge on the base is going to grab the hydrogen and go fishing for it. Those electrons go on to the nitrogen. And if you remember, nitrogen likes to make 3 bonds normally, so it's still going to make the 3 bonds, but now it's gotten its lone pair electrons back. So it won't be charged with a negative charge. It'll just have that neutral nitrogen. So that is how we would do number 18. For number 19, we draw the conjugate acid for each of the following bases. In this case, what we're given here is the base, and it's going to pick up a proton. So we have some form of H+ available. So water is the one acting as the base, so I have the lone pair electrons. So in this case, our base isn't negative, but it is partially negative. These electrons can go fishing for a hydrogen here. And this is the proton that was picked up, and we have H3O+. So that would be our conjugate acid. A lot of times H+ will be abbreviated for, or H+ is an abbreviation for H3O+. So H+ can equal H3O+. So H3O+ here is our acid. Again, our alcohol is our partially negative base. The lone pair electrons from here can grab this hydrogen. Those electrons can go on to the oxygen. So we've picked up a proton here, and there is our conjugate acid. In number 23, we're looking to identify the more stable anion. So this is asking which one is better at holding the negative charge. So we have in example A, a negative charge on a carbon and versus a negative charge on a carbon. This one, it has a carbon with 3 sp3 carbons attached to it, and this one has 2 sp3 carbons and an sp2. If you recall, when you have a negative charge next to a double bond, this is allylic. This is allylic. And when you have something with an allylic negative charge or a positive charge, we have the possibility here of resonance. So we can shuffle those electrons around. I can move these electrons into this bond and these electrons from the bond onto that carbon. So my double bond would move here and the electrons would go here. I would not be able in the first structure to draw a resonance because these are all sp3. And likewise, I can't draw resonance structures into this carbon or this carbon for the same reason. Those are sp3, They have full octets, so we don't want to push electrons into there. Because we have resonance structures, this second one is more stable. So that guy is more stable with its resonance. In the case of the second one, we're going to look at a carbon negative versus a carbon negative. This is an sp2 carbon. This one is sp. So there's more electron density with the pi bonds. And so the orbital indicates, the extra orbital indicates that this one is more stable. In this one, we're looking at which is the more acidic compound. So I'm comparing a benzene ring, or a six-membered ring with pi bonds, versus this one over here. This one is more acidic. We have the same atom, but this one has the possibility of resonance and also orbitals. In this second example, we have that same six-membered ring with the alcohol. And on the first ring, we have chlorines all around versus carbons. This one will make it more acidic because of the electron withdrawing chlorine. So this is induction. And then in this case, in G, our acidic proton is this one next to the hydrogen versus this H next to the carbonyl versus all of these. These are your sp3 carbons. If I were to draw the conjugate base versus, let's say it took that one, I have a C- in both cases, but this one here has a resonance possibility. So this one is more acidic. These are similar problems. We're going to look at the more acidic compound. And here you can evaluate by the negative charge. In this case, because the nitrogen seems like it would be better at taking the negative charge, there's two pi orbitals here on the alkyne. So this one happens to be the more stable one because it has the orbitals. Whereas the N atom by itself is not going to be able to do that. In G, we're looking at a triacid. A triacid is 3 carboxylic acids. I'm looking at comparing this one. We'll call that A, B, and C. If I was going to rank them from, in order to find the most acidic one, I want to find the differences between them. So A is next to, the hydrogen here is next to a carbonyl with 2 chlorines. C has no chlorines here. And then B has these carbons over here. So the one with the electron withdrawing groups, drawing electron density out, is going to be the most acidic. So A is the most acidic. In this problem, we're going to look at the reaction with water. So all of these are acting as the base. That means waters are acid in all of them. And I'm going to draw the arrow mechanism for that. In the first one, the negative charge of the base is going to grab the proton. That electron goes onto the hydrogen, or onto the oxygen. So I'd have a hydrogen here, and that becomes OH minus. In C, we have the same arrow drawing. The electrons go on to the hydrogen. The electrons will fish for the hydrogen. Those electrons go on to there. So we get our hydrogen on the benzene ring. Plus OH minus. And in this case, our negative charge is again going to go fishing. We have the hydrogen there. And our OH minus. Here we're drawing our mechanism arrows again. Got to figure out which one is the base. The base is the one with the negative charge. This is our acid. Conjugate base. Conjugate acid. So I can kind of cheat and see what is being removed from the reactant here. So this sulfur S minus is going to grab the hydrogen here. Those electrons go on to the sulfur. And I get S minus. The side that is going to be favored, if I compare the pKa's, I don't know that I can because I don't remember seeing pKa for H2S or SH here. So I'm going to go with the ARIO method and look at which one is our bases. I'm going to compare my base of the S minus versus the S minus over here. The atoms are the same. And so I'm going to go next to resonance. And based on resonance, I can draw resonance structure with this guy right here, but not with the other one. So this side is more stable. That one will be preferred. In the second example, water is acting as my acid. This is my base. So this is the conjugate base. Conjugate acid. I'm going to draw my arrows. And then I'm going to look at pKa's to decide which one is favored. This is another one where they're very close to each other. The alcohol pKa. Water is 15.7. Alcohol is around 16. So it's very slightly more preferred here. If I look at the ARIO, I have an atom of oxygen versus oxygen. And the negative charge will be stabilized by OH just a little bit better because it doesn't have the extra electron density. So this one is favored here. Okay, in this reaction, we're looking at identifying the acid and the base. We have to draw the products. When you have lithium or sodium paired up with OH, lithium is a cation, so that's going to be Li plus, which makes OH minus. So this is my base. This is synonymous with sodium hydroxide, so this is my base. So when I draw the products, I know my base has to grab the most acidic proton, which is this H right here that's kind of sticking off there. And those go on to there. So I'll have a minus charge on that carbon versus with water here. This is my conjugate acid. This is my conjugate base. That one's the acid. Okay, so I've labeled all of those, drawn the curved arrow, and now I need to figure out which side of the equilibrium is preferred. So I want to compare my bases. I have an OH minus versus a C minus. And this is C can also, the oxygen here, if I draw a resonance structure, would be the one holding the charge. So this is preferred. So this one has resonance. And the atom. Because if I draw the resonance structure, which would be this right here, I would have the negative charge on the oxygen as well as the other one, plus I have the added resonance. The pKa of water is around 16 or 15.7. The pKa of carboxylic acid is around 5. So again, that one points to that being favored. In this example, I have two different acidic protons possible. I have this one here and this one that is in between. The pKa of this, I'll call it HA, is around 9. This one, which is B, is around 20. So the base is going to grab the more basic, or the more acidic one, which will be this guy right here. So it's going to take this. Those electrons go on to that carbon. And I get water here. So I can compare pKa's. So the pKa of this one was around 9, and the pKa of water is 15.7. So that would indicate that the product side is favored. Or I can look at ARIO. I have carbon negative versus carbon negative. I have oxygen minus versus carbon negative, but this one also has resonance, where I can spread it actually if I draw the hybrid resonance across 5 atoms. So this side is preferred. Here we're looking at pKa values for the following constitutional isomer. Salicylic acid is the precursor for aspirin. And then we have para-hydroxybenzoic acid, which may appear in some of our biological pathways. So using the rules that we developed in this chapter, we might have expected these two compounds to have similar pKa's. Nevertheless, they are different. Salicylic acid is more acidic than its constitutional isomer. Can you offer an explanation? So the structures are pretty much the same. The only difference is that in salicylic acid, our OH is next to the carboxylic acid. And in the other one, it is far apart from here. So how can we explain the pKa of salicylic acid being much more acidic versus this one here? This one has to do with the proximity. If I drew out the OHs here, you can see that they are close together. And if this was to become an O minus, it would have hydrogen bonding here that could help support that charge and stabilize it. in addition to all of the resonance structure, whereas if this para-hydroxybenzoic acid became the anion, it would not have the same support. So this has to do with proximity. And those are the chapter 13 problems.